Hi everyone. So I welcome you all to the seventh lecture of the structure of atom. So myself, I am a Varad Daoo, a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous classes, what we have seen is we have seen about the classical wave theory and particle theory for electromagnetic radiation. We studied that the classical wave theory could not explain photoelectric effect and black body radiation emitted by the electromagnetic radiation, and hence we concluded that light or electromagnetic radiations are not only particle but also they are not only wave-like, they don't have only wave-like behavior but also particle-like behavior, which could be explained, which can explain the photoelectric effect and black body radiation. Further, we learned about the Planck's quantum theory of radiation, and then we also solved some couple of examples based on this, and then we also studied about the atomic spectra, and of atomic spectra we studied about the emission spectra, right? So let me recap, right? So let us start. This is lecture 7, structure of atom. What we are going to study today is atomic spectra. So we studied about what is atomic spectra. So there are two parts of it. One is emission spectra and the other is absorption spectra. Right? So we already studied about the emission spectra, but just to recap, I will say that emission spectra are obtained when the radiations emitted from substance that have absorbed energy either by passing electric discharge through a gas at low pressure or by heating the substance to a high temperature are analyzed with the help of spectroscope, right? The atoms, molecules or ions that have absorbed radiation are said to be excited, right? Right. For example, when the gases or vapor of chemical substances are heated by electric spark, a light is emitted, and the color of light depends upon the substance under investigation. So such a spectrum of line, right? The emission spectra obtained by analyzing radiations emitted by passing electric discharge through hydrogen gas at low temperature, right, is for this. So the emission spectra is like this. Right? What we have in here is these are the tubes, right? This is the electric circuit. These are now the slits from where the light is going to pass. Right? So this is the direction of light. So this is the direction of light, right? It is going to pass through the slit. Right? So this is it's a different color. So this is a slit, right? And this is the discharge tube containing hydrogen, right? So when this passes through prism, right? This is the prism. So when light through this passes through this prism, it splits into various components, right? This goes to a screen, right? So this is the screen which we have, right? This is the screen and this is the prism, right? So the spectrum which we obtained is called as electromagnetic spectra, is called as emission spectra, and the nature of this emission spectra is like this, wherein we have these lines, right? So what is this? This is going to be red light. Let's say for example, for hydrogen atom, for hydrogen gas, that's going to be violet, right? And this is called as emission light spectra, or only light spectra, light spectra. And this whole setup is called as the emission spectrum of hydrogen atom, right? So now let us study about the second type of spectrum. It is called as absorption spectrum, right? So this one, first one was the emission spectrum. Now is the light spectrum. Oh, sorry, the absorption spectrum. So when a continuous electromagnetic radiation, let's say it to be a white light, is allowed to pass through a gas or a solution of some salt and transmitted light is analyzed, we obtain a spectrum in which dark lines are observed in an otherwise continuous spectrum, right? So these dark lines indicate that the radiations of corresponding wavelengths have been absorbed by the substances, right? So such a spectrum containing a few dark lines due to the absorption of light is known as absorption spectrum. So to understand it, let me draw a diagram. What we have is a slit like this. This is going to be a slit, right? This is a slit. This is going to be a light, sunlight, right? It is going to pass through the a beaker containing NaCl solution, right? Let's say it's like this. This is NaCl solution. This is light, and these are the slits, right? Right. Now let passes through this, right? Then it passes through the prism, right? Just like in emission spectrum, right? Then this light splits, right? And then it passes through the screen, right? So this is the screen. So this is the screen which we have, and this is the prism, right? So the spectrum which we obtain in this setting is called as absorption spectrum, and it has these dark lines in it, right? Like this, right? Dark lines. This is called as, right? So this whole full assembly is known as absorption spectrum of sodium chloride, right? So what we have is spectrum containing a few dark lines due to absorption of light is known as absorption spectrum. right? The dark lines, let me write it as number 1. Number 2, characteristics of this spectrum. The dark lines are of definite wavelength and are also characteristics of the substance. Right? It may be noted that these dark lines. So when we say dark lines, I am meaning these dark lines, right? So so these dark lines, right? So these are the characteristics of substances. Right? These dark lines appear exactly at the same place where the lines of emission spectra appear. Right? Lines in right? Lines of emission spectrum appear, right? For example, the emission spectrum of sodium consists of two important yellow lines at 589 nanometer and 589.6 nanometer, right? On the other hand, when white light is passed through vapor of sodium, we get dark lines in the absorption spectrum at the same place, right? That is at 589 nanometer and 589.6 nanometer. Right? The study of emission or absorption spectra is called as spectroscopy, and this has become very important and essential field for all chemists. It helps to study the electronic structure, right? These characteristic lines in atomic spectrum can also be used in chemical analysis to identify the elements, right? So the study of emission or absorption spectrum is called spectroscopy, right? So why is there this or? This is because both of these methods are contemporary to each other. It is not important to study both of these things, both the emission spectra and the absorption spectra. We don't need to study both of them. We can study either one of them because both of them give us the same information, right? So now let us understand the difference between emission and absorption spectra. Emission and absorption spectra. The difference is here we are going to write emission spectra and here we are going to write about the first point is emission spectrum is emission spectrum is obtained when radiations emitted by the excited substance are analyzed with the help of spectroscope, right? Whereas absorption spectrum is obtained when the white light is first passed through the substance in gaseous state or in solution and the transmitted light is analyzed with the help of spectroscopy, right? Emission spectrum is obtained when radiations emitted by the excited substance are analyzed with a spectroscope. Absorption spectrum is obtained when the white light is passed to the substance either in gaseous phase or in solution, right? And the transmitted light is analyzed spectroscope. Second point is emission spectrum consists of emission spectrum. Emission spectrum consists of bright colored lines separated by dark lines, whereas absorption spectrum consists of dark lines in an otherwise continuous spectrum. So emission spectrum consists of bright colored lines separated by dark spaces, whereas absorption spectrum consists of dark lines in an otherwise continuous spectrum, right? So now the next topic which we are going to study is emission spectrum of hydrogen atom. The spectrum of hydrogen atom has played a very important role in the development of atomic structure. The spectrum of hydrogen atom can be obtained by passing an electric discharge through the gas taken in the discharge tube under low pressure. The emitted light is analyzed with the help of spectroscope. Hence, the why is that? Because we are using the emission spectrum, right? The spectrum consists of large number of lines appearing in different region of wavelengths. Some of the lines are present in the visible region, while the other are present in violet or infrared region, right? Right. The emission spectrum of hydrogen consists of a large number of lines appearing in different regions of wavelength. So some of these lines are present in the visible region, while the while others in the ultraviolet and infrared region, right? Okay. So the equation which was developed was, so let me write. So in 1885, J. Balmer developed a simple relationship among the different wavelengths different wavelengths of the series of visible lines in the hydrogen spectrum, right? So this expression is very important. So the expression is 1 by lambda, which is nothing but wave number, which is mu bar in centimeter inverse, is nothing but 109677 into 1 by 2 square minus 1 by n square, right? Where n is an integer equal to or greater than 3, right? that is n can take value 3, 4, 5, etc. And this expression is known as Balmer formula. Right? However, the main limitation of this expression is that it gives lines only in the visible spectrum, right? Balmer formula gives only the spectral lines in the visible region, right? And these series of lines which appear in the visible region are named as Balmer lines, right? These lines or these series of lines which appear in visible region were named Balmer lines. Soon afterwards, a series of spectral lines of hydrogen atoms in different regions were discovered. These lines in different regions were grouped into 5 different series of lines, right? And each line being named after the name of its discoveries, right? So these lines are, let me write it down, different lines or spectral lines for hydrogen atom. So these series of lines which I am writing, right? Spectral lines. So number 1 is, so here I am going to write which series it is. Then here we are going to write region, whether it's in ultraviolet region, infrared region, or visible region. Then and here we are going to write something called as N1 and N2, but we'll look at it afterwards. The first is the Lyman line, and this belongs to ultraviolet region. The second is Bauman line, and it is a visible region. The third is Austen line in infrared region, bracket lines. These are also in infrared region. And then fund lines. So this is spelled as PFUND. These are also in infrared region, right? And the expression like similar to this Balmer formula for all other, there is a generalized expression for all of this, and that generalized expression is 1 by lambda is equals to in, so this is wave number which is nothing but r into 1 by n1 square minus 1 by n2 square, where r is nothing but constant and its value is 109677 centimeter inverse, and n1 n2 are the integers where n2 varies as n1 plus 1, n1, n1 plus 2, n1 plus 3, so on and so forth. And to get the Lyman series line, we have an n1 value of 1 for this, n2 value could be like has been mentioned here, right? Like has been, if n1 is 1, n2 can be 2, 3, 4, 5 as per this expression here, right? Right, this has to be 2, then this can be 4, 5, like this. This is 3, this is 4, 5, 6, right? This is 4, so this could be 5, 6, 7, right? This is 5, then this 6, 7, right? Like this. And but this is valid only for hydrogen atom, right? So a slight correction in this formula could lead us to hydrogen-like atoms, right? Right. So let us first write this down. So it may be noted that the above equation is true only for spectral lines of hydrogen atom or hydrogen-like atoms, right? So hydrogen, right? So this is the expression only for the different series for hydrogen atom, right? Not this one only for hydrogen atom, right? So if we add one more, that is, if we add in here one more term, then what we can have is we can have a so let me just write it down. For hydrogen like atoms, hydrogen like ions, right? For example, right, like this At plus or Li plus 2, the above expression changes. Expression changes as, right? In that case, 1 by lambda is going to be mu bar, which is wave number, which is R into 1 by n1 square minus 1 by n2 square. So here just we are going to add a z square, where z is what? Nuclear charge. For helium plus, z is going to be 2. For Li plus 2, z is going to be 3, and so on. Right? So this is the general encompassing equation. If you want for hydrogen, we just put z is equal to 1, and if you want, let's say a Lyman series, we put n1 is equal to 1 and n2 could be 2, 3, 4, 5 up to infinity with numbers, right? So based on this, let us solve an example, right? So the first question which we are going to solve is, what is the wavelength of light emitted when the electron in the hydrogen atom undergoes transition from an energy level with n is equal to 4 to an energy level with n is equal to 2, right? And this is the first part. The second part is, what is the color of the radiation? What we have is, according to, so we are going to solve it based on for hydrogen atom, right? So according to equation, what we have is 1 by lambda is mu bar in centimeter inverse is nothing but r into 1 by n1 square minus 1 by n2 square. So what we are given is, we are already given n1 is equal to 2, n2 is equal to 4, and r is equal to 1096,777 is centimeter inverse, which means 1 by lambda is nothing but we just put in the values, known values, to get this expression. Okay. 1 by 2 square minus 1 by 4 square in centimeter inverse. This corresponds to 1 by 4 minus 1 by 60. And when you simplify it, we get it as 4.86 10 raised to the power minus 5 centimeter, which corresponds to about 486 nanometer, right? Sorry. So this is not this. This means lambda is, so this implies lambda is nothing but this, right? So this is one of the value. And since what we are doing, we are dealing with hydrogen atom, and we know n1 is nothing but 2, right? So from this table, what we see is when n1 is equal to 2, we are in the Balmer series and the region is visible, right? So we are in the visible region, and in order to, so we are in the visible region. Region is visible region, and invisible region, if you want to find out whether it's towards red or towards violet, then we will have to look at the electromagnetic spectrum, and when you do that, we see that this is bluish green color, right? So this has also has to be marked, right? So the next question, question 2, right? Right, so what we have is equation, spectral line corresponds to n1 is equal to 3 and n2 is equal to 5. So what we are asked is calculate the wavelength and frequency of this radiation or of this spectral light. So we already know that 1 by lambda is nothing but r into 1 by n1 square minus 1 by n2 square. Here we are given n1 is equal to 3, n2 is equal to 5, and we already know the value of r, which is 109677 centimeter inverse. We plug in the values, what we get is 1 by 3 square minus 1 by 5 square. So when you do the calculation, it turns out to be 1282 10 raised to power minus 5 centimeter, which is nothing but when you convert it into nanometers, right? This corresponds to 1282 10 raised to power minus 7 meter, and this is 12.82, right? 1282 into 10 raised to power minus 9 meter, which is nothing but 12 nanometer, right? And then we also know that lambda into frequency is nothing but speed of light. This implies frequency is c by lambda, which is 3 into 10 raised to power 8 meter per second divided by 1282 10 raised to power minus 9. Hence we get frequency as 2.64 to 10 raised to power 14 second inverse, right? So now moving on to the third question. This is a very important question, right? What we have is what transition in the hydrogen spectrum would have the same wavelength as the Balmer transition, right? So we are given 2 n is equal to 2 of He plus spectrum. So for He plus spectrum, what we have is as it's a hydrogen like ion, what the expression which we are going to have is this one into z square, right? So here in the previous, right, this expression is what we are talking about, right? And we already know that for He atom it is given z is nothing but 2, right? So we are going to utilize this. So for hydrogen atom, we are given n is equal to 4n. So what we are given is n1 is equal to 2, n2 is equal to 4n, z is equal to 2. So 1 by lambda is r into 1 by 2 square minus 1 by 4 square into 2 square, which corresponds to 1 by lambda is nothing but 3 by 4r. This is expression 1, right? So for hydrogen atom, what we can do is we have 1 by lambda is r into 1 by n1 square minus n2 square, right? Now since this is expression 2, so since lambda is same, we are going to equating equation 1 and 2, and hence what we get is 1 by n1 square minus 1 by n2 square is going to be 3 by 4, right? Now we know that this n1 and n2 has to be integer values. So for this we put in the uh, heat and trial, right? So we also know that it's a Balmer series, right? For hydrogen, it's going to be Balmer series. That means n1 is going to be 1. This turns out n2 is going to be 2, right? Therefore, the transition from n is equal to 2 to n is equal to 1 in H atom will have the same frequency, will have the same wavelength as the transition from n is equal to 4 to n is equal to 2 in He plus, right? So this is our result, right? Right. So the next topic which we are going to study is the drawbacks of the Rutherford's model, right? I'm just going to give an overview of this. So according to Rutherford model, an atom consists of a heavy charged particles, heavy charged, heavy. Okay. So according to Rutherford's model, an atom consists of a heavy positively charged nucleus surrounded by a negatively charged electrons moving around it in a circular path, right? So this model was analogous to the solar system, where the nucleus may be compared to the sun and the electrons to the planets. The Coulombic force between the nucleus and the electron would be given by this expression, right? Q1, Q2 by R square, where Q1 and Q2 are the charges and R is the distance of separation between the molecules and the electrons, and K is the proportionality constant, right? And this is similar to the gravitational force between two masses with mass m1 and m2, and the force would be in that case g m1 m2 by r square, right? Where g is the gravitational constant and r is the distance of separation between the planet. However, there is an important difference between the solar system and the nuclear model. The electrons have extremely small mass and are negatively charged, whereas planets are massive and neutral, right? The planets involved in well-defined circular path around the sun, right? So this is also true that the planets revolve in well-defined circular path around the sun. However, there arises a difficulty with Rutherford's model, right? So it failed in the light of electromagnetic principle, right? It was shown by Maxwell that a charged body moving under the influence of attractive forces loses energy continuously in the form of electromagnetic radiations, right? Thus, unlike a planet, the electron is a charged body and thus it should emit radiations while revolving around the nucleus. As a result of this, the electron should lose energy at every turn and move closer and closer to the nucleus following a spiral path. So what basically said is, although that the uh, force acting between the electrons and nucleus is similar in nature to the gravitational force which is acting between the planets. The main problem with the Rutherford model was that it was shown in by Clerk Maxwell, that when we have an electric field and when there are two charges with the opposite spin and they are revolving around each other, then the charges should emit radiation and hence the energy should be decreasing with each rotation, and hence the positive charge, the negative charge, that is electron, should somehow collide to the nucleus. So the figure would be, let's say this is the positive charge, that is the nucleus, and this is the electrons, right? So this is revolving around the revolving around the nucleus in, let's say, this fashion, right? So this, let us remove it and let us say that this is the nucleus which we have. This is the nucleus, right? Let's say this is positively charged and there is an electron right? So it is getting attracted in this force and it's moving along this direction, right? So because the force here is the electromagnetic attraction, what Clark Maxwell showed is that when this complete rotation, so it will not be like this, it should be, because energy is being lost by this electron, because it is going to emit radiation, the path will not be a complete circle, and instead it will be like this. It will be moving, let's say like this, and it will be like this. The path should continuously decrease and eventually the electron should lie on the, should collide with the nucleus, collapse on the nucleus, right? So this was not the case, right? This was one of the major drawback, right, of the Rutherford model, right? Then consequently the orbit will become smaller, like I have said, the orbit should become smaller, and consequently the orbit will become smaller and smaller, and finally the electrons would fall onto the nucleus, right? So in other words, the atom should collapse, and the calculation have shown that it takes only about 10 raised to power minus 8 seconds to happen this, right, for an electron to spiral into the nucleus, right? However, this does not happen. Therefore, Rutherford's model cannot explain the stability of atom if the motion of the electron is described on the basis of classical mechanics and electromagnetic theory of electromagnetic theory, right? Hence, Rutherford's model cannot explain, cannot or could not explain the stability of atom. Obviously, we may think that if motion of electrons in orbitals in orbits lead to a instability of atom, then why not consider electrons as stationary around the nucleus? However, if the electrons were stationary, electrostatic attraction forces between the nucleus and the electrons would pull electrons towards the nucleus to form a model as described by J.J. Thomson, right? Hence, Rutherford's model failed to explain the existence of certain definite lines in hydrogen spectrum, right? So the other drawback was that Rutherford's model failed to explain the existence of certain definite lines in the hydrogen spectrum, right? If the electrons were to lose energy continuously, the atomic spectrum of hydrogen should have been continuous. However, the spectrum of hydrogen has been found to be discontinuous in the form of characteristic lines of definite wavelengths, right? This is the other serious drawback of the Rutherford model, right? Hence, this model does not explain the structure of atom, that is distribution of electrons around the nucleus and this energy, and thus we need a better model, and that model has been given by Bohr, which is what we are going to study in the next class. But before that, let me write this down. Bohr to lose it. The electromagnetic spectrum, sorry, the emission spectrum, the atomic spectrum, hydrogen should have been continuous, right? However, we found that the spectrum of hydrogen is not continuous, right? Hence, now the next step which we are going to study is Bohr's model. Next model is Bohr's model. Right? So let me do the summary. So in this class, what we have seen is we have seen that atomic spectrum has two types. One is absorption spectrum and the other is emission spectrum. We studied its similarities and differences, and we also concluded that both of these techniques are complementary. That is, we need not study both of the spectrum. Any one spectrum will give us the essential and as information, right? Then we studied about emission spectrum of hydrogen. Then we studied about 5 different lines, right, which are Balmer region, Balmer lines, or one lines, right? Or should I write this like Lyman lines, Lyman series, Balmer series, Paschen series, Pound series, and Bracket series. Right? Then we studied about the for different lines, for different series of lines, and for hydrogen-like species. Then we solved some example based on this concept, and finally we studied about the drawbacks of the Rutherford model, which are that it could not explain the stability of atom, right? And hence there was a need to develop a new model, which is called as, which was given by Bohr, right? And this is what we are going to study in the next class. So I hope you enjoyed this lecture and you gained enough knowledge. And I hope to see you again in the next class. And thank you for attending this lecture. Right? I hope to see you in the next class as well. Thank you.